Let's consider a current through a solenoid. Now, if this current is a constant, it doesn't change with time. If it is DC, then the flux produced will be constant. But if it is changing with time, the flux will also change with time. So, if di over dt is non-zero, then the flux that is produced, that is d phi over dt, is also non-zero. Now, we know from Faraday's law of electromagnetic induction that because of this changing flux, an EMF will be induced in the across the coil, which will be as such that it will oppose the cause of its production. So basically, let's say this current is going in this direction, the current, and the flux as a result, let's say it's going downwards. Now, if the current is changing, if it is increasing with time, then the flux is also increasing with time. So the produced EMF will be as such that it will try to oppose the change of flux, because that's the cause of its production. So it will be as such that it will try to produce a flux in the other direction, in the opposite direction, in upwards. So it will try to produce a current. In order to do that, it will actually, the EMF produces a current, so it will try to produce a current in the opposite direction, that is in this direction. So the EMF will be like that. So we know the expression given by Faraday's law is the induced electromotive force is E is equal to N d phi over dt, so rate of change of flux times number of turns, and there is a negative sign, which means that it is in the opposite direction basically. So that's the induced EMF, or the voltage as produced as a result, induced voltage basically, and it is in direct proportion to the rate of change of flux. So if the flux is changing very fast, the induced EMF is higher, and if it is changing slowly, then the induced EMF is lower. So we can introduce another term, L, inductance, and we can see that actually the induced voltage is in direct proportion to current, basically rate of change of current, because phi is rate of change of phi is proportional to rate of change of current. So we can say VL, which is the voltage across the solenoid, is proportional to di over dt. And if we see this as an inductor, we can inductance basically, we can introduce the term inductance as the property, and we can equate this to the voltage. Inductance times rate of change of current is equal to VL, and if we do that, then this is actually our VL as well, because this is basically the induced EMF, induced voltage. So VL is equal to N d phi over dt. We can do away with the negative sign because that only gives the direction. So this is equal to this. So we can say L di over dt is equal to N d phi over dt basically. From here we can see that L is equal to N d phi over di. So basically rate of change of flux with the rate of change of current, how more it's changing. So if the material is of a high inductance of the inductor value is higher, then with small change of current, the change of flux will be more, and if it is of a lower quality inductance, the change will be less. So basically this is just the inductive property of the inductor. And also in terms of material dimension and property, we can get the value of inductor of a solenoid. I won't deduce that, but this is like that. Mu, which is permeability, times N square times over L. So mu is the permeability of the material, so that is relative permeability times permeability of air. Relative permeability of the material times permeability of the air, that's the permeability here, and then number of turns squared times cross sectional area which is this cross sectional area, and then length, over length. So if it is longer, then less value of inductance, and inductor value is less, and if it is smaller, then higher, like that. So that's what it is. So basically, rate of change of current, if it is of higher value of inductance, then it will oppose the change of current even more. So if we go into a circuit with an inductance, if we say we have a DC circuit here, and there is a switch here, and this one, and then the inductance, a resistance and inductance, and RL circuit, basically this is E, this is R, and this is value of L, and if at t is equal to 0, this switch is closed. What happens is the current cannot achieve its steady state value instantly. It takes a while because of the inductance, because inductance opposes the change of current. It is the induced voltage in the inductance that we were talking about, the voltage that we get from Faraday's electromagnetic induction law. It actually opposes the change of current because it's trying to oppose the change, oppose the reason that is causing it, basically. So the current takes a while to achieve the steady state value. The steady state value will be just defined by the resistance and the applied voltage. So this is how it achieves the steady state value. So that one is E over R, this is I, and this is T. So this is just the transient response, and the time constant here is L over R. So basically I will be E over R 1 minus e to the power minus t over L over R. So becomes t times L, because the time constant is in the denominator of the exponential here. So yeah, like that. And if it is of a higher inductance, it takes a longer time, and if it is a smaller inductance, it takes, so this is less L, and this is so if this is L1, if this is L2, so L2 is greater than L1, like that. So yeah, this is just an introduction to inductance, basically, this video.